Hello, shortly we're going to get started with our webinar Next on the Pad. We welcome you to the virtual small satellite conference. I'm Charles Swenson. I'll be the MC for today's webinar, and we're going to wait a minute or so before we get started just to see. We still have people joining the Zoom webinar, and it takes a minute or two before we get people in. Okay, we have over 100 people in the webinar at this point, and as I said, I'm the Master of Ceremonies, Charles Swenson, Utah State University, Associate Chair for the Small Satellite Conference, and I would like to introduce our moderator for today's session, Roger Hunter. Roger is the program manager for the NASA Small Spacecraft Technology Program. His career, he spent 22 years in the Air Force and a brief stint at Boeing before going to work for NASA. His first assignment, or previous to taking over the lead for the NASA Small Spacecraft Technology Program, he was the program manager for the NASA Kepler mission. I'd like to briefly share my screen here to show our list of presentations today. These are the talks and the individuals that we have in our panel, and I will let Roger introduce them to you. We'll go through and let them each take a minute and give a brief overview of their paper, and then eventually we'll open up for questions. As you want to ask questions, you'll want to go down to the lower right-hand corner of your screen. There's a Q&A box. Please use the Q&A box. Bring that up, type in your questions, and we'll have, Roger will be asking the questions and directing them to the various panel members. And at this point, I think we're going to turn it over to Roger and let him introduce our panelists.
Thank you, Charles, and also thanks to Marianne Sidwell for helping with the logistics for this afternoon. The first speaker we're going to have is going to be Ensign Angeline Knight from the U.S. Navy, and she's going to be giving us a thumbnail sketch, first of all, of their paper, which is entitled Design and Development of On-Orbit Servicing CubeSat Class Satellite. So, Ensign Knight.
Hi, good afternoon. I am with the Naval Academy Satellite Team for Autonomous Robotics, also referred to as NSTAR. So in a summary, the written paper discusses NSTAR's second iteration project. So the Robotic Experimental Construction Satellite, we refer to it as REX, is a 3U CubeSat class satellite with 2 extendable 3D printed robotic arms. Each arm has 6 degrees of freedom from 7 motors. REX is designed and developed for future integration aboard the International Space Station. So that's where it will be undergoing a series of tests designed to establish some of the initial autonomous operation capabilities. So the flight load itself consists of 2 of the duplicate REX systems placed inside a guarded system enclosure, and that's there for protection purposes from external disturbances from astronaut movement aboard the ISS. But essentially, REX's purpose is to fulfill those initial capabilities of an autonomous construction and repair satellite, such as pointing accuracy, object tracking, manipulation, and inspection. And so as of now, REX is scheduled for launch in the spring of 2021. So that's the main summary. Look forward to hearing your questions.
Okay. Ensign Knight, I had one question, because one of the things I noticed as I watched your talk was that many of the cadets or midshipmen, I should say, sorry.
Yes, sir.
Sorry, I was in the Air Force for a while. Many
We'll let
of
it
the
slide.
men who were working on this have graduated and moved on to assignments. So I was intrigued by how did they capture the knowledge and experience that was used in moving this project along, and as they transitioned it to those who are going to actually see the fruition of it on board the ISS.
Okay, so we were lucky enough to already kind of start that transition prior to January, as we had some juniors kind of working along in the hindsight with our project, just because we kind of anticipated that this project would be carrying on past our graduation date. Granted, the COVID-19 epidemic kind of made things a little more difficult as we weren't physically present, but we've managed to have weekly talks, and we're still in constant communication. And I just graduated in May, and so I'm still attached to the Naval Academy in October, and so we're just kind of leading them along until we detach, but they're fully capable of being able to take on this project and see to the launch in the spring of 2021.
Okay, thank you. What we're going to be doing for the rest of the session is that we're going to go through each speaker and give them also another minute to introduce their paper, and then we'll offer a question. Then we're going to come back to everybody so that as we get more questions into the chat zone, we can spread the questions around to all of the speakers. So hang in there. Next up, I think Bill Denninger has joined us, and he is with the Ball Aerospace and Technologies Corporation. And he's going to give us a thumbnail sketch of the Small Satellite-Based Imaging X-ray Polarimeter Explorer mission. Bill Denninger, are you there?
So we may be having some technical problems with Bill. Bill, if you can't work it out, you could always phone in using the number for the Zoom meeting. We'll try and circle back to you.
Okay, let's see if Bill can get his audio and video corrected. Let's go to the next speaker, which is going to be Maddie Garcia from Massachusetts Institute of Technology, and she's going to be giving us an introduction to BeaverCube, the coastal imaging with visible and long-wave infrared CubeSats.
Yeah, so BeaverCube, so I'm Maddie Garcia. I'm working with MIT Starlab under Dr. Carrie Cahoy. So BeaverCube is a 3U ocean imaging CubeSat. BeaverCube is primarily developed by undergrads in the Space Systems Development Capstone Project. So currently we are also facing a similar problem of migrating undergrads over the summer and continuing the project with other graduate students. So BeaverCube, as I said, is a 3U ocean imaging satellite. The goal of BeaverCube is threefold. So we're looking at cloud top temperature and sea surface temperature in the eastern coastline range in order to identify marine heat wave patterns and warm core ring currents. We're planning on overlaying visual imagery as well to identify associated organic matter blooms with the different temperature differentials. We are also looking to demonstrate the operation of the Axion tiled ionic liquid electrospray technology for orbital maneuver changes. And additionally, as mentioned earlier, serve as an educational exercise for students.
Thank you. I was intrigued by the use of the Axion tile system because we're working with them on another project, and it's a different variant. So I noticed that you're going to be doing that at the end of the demonstration of your spacecraft. Is that correct? And I saw the talk, and it indicates you're doing orbit raising. Is there consideration of doing orbit lowering with the thruster system instead, even though it's only about 280 meters? I think it's very small orbit change.
Yeah, so as of right now, we're just doing orbit raising, one thing at a time, because this is Axion's first flight. So yes, we'll just be doing, as you said, 280 meter orbit maneuvering or translational maneuvers, looking at a retrograde orbit. So hopefully we're able to fire in the exact line of orbital velocity in order to get that 280 meter change. But yeah.
Awesome. Let's go see if we can go back to Bill Denninger. Bill, have you been able to correct your audio and video?
I believe I have. Can you hear me?
Yes, thank you. Yes, so once again, Bill is going to give us a quick overview of his talk, the Small Satellite-Based Imaging X-Ray Polarimeter Explorer.
Thanks very much for that. The Imaging X-Ray Polarimeter, for short, is a NASA Small Explorer mission. It's a SMEX. We're specifically going to be looking at the effects of gravity, energy, and electromagnetic fields at their extreme limits. It's pretty cool stuff. What we're going to do is we're going to be adding X-ray polarimetry to examine X-ray sources that are known. We'll be looking at things like neutron stars and stellar mass black holes, supernova remnants, that sort of thing. Prior missions have looked at large-scale imaging. They've looked at spectroscopy. They've looked at timing, and they've looked at energy. IXPE is going to add polarization degree and polarization angle to that suite of measurements, which has only been done once before in 1975 on the OSO 8 mission, which had to share its aperture with 8 other instruments, so there's very little viewing time. Interestingly enough, the PI for this here in 2020 was the PI for that mission in 1975, Martin Weisskopf. We also have an imaging capability because we have a fairly narrow focus of our X-ray optics, so we're going to be able to image extended objects. We're going to use 3 imaging X-ray telescopes. The optics are provided by Marshall Space Flight Center, and they're assembled in final test at Marshall. The instrument, along with the detector units, are from our Italian partners. That's been delivered to Ball and is undergoing bench acceptance tests. And the boom used to establish the focal length is at Ball and already integrated onto the spacecraft. We're using a Ball small commercial platform called the BCP configurable platform. It's going to be the 4th build of that platform. Yesterday in the year in review webinar, the GPIM mission was covered, which is the 3rd build of that platform. The IXPE spacecraft's complete, and we did initial power on with flight software load in June. IXPE is going to be doing world-class science on a small explorer's budget with a small spacecraft. Thanks.
Okay, thank you. I noticed that your partners do include a contingent from Italy. Did you guys have any issues with COVID-19 during the assembly integration test or build up to the spacecraft?
I think like everybody else at this mission, COVID-19 has been a joy for our mission. Specifically at Marshall Space Flight Center, they're a NASA center, so they had to follow the NASA rules, and they went into a level 4 shutdown where they really couldn't get any work done. That was partially lifted where they could get task by task approval to do work on the X-ray optics starting in late June. So they were able to start rebuilding items at that point. So that pushed them back in their deliveries by several months. Our Italian partners were able to finish the instrument right before the Italian government shut down laboratories and closed their borders. They were able to ship a detector unit engineering model to the United States so we could start doing some initial work, but they weren't able to get the actual flight instrument here until they were allowed to go back into the facilities and ship items. Ball, since it's an aerospace company, was designated one of those critical companies, and we were able to continue working here and maintain our progress and get pretty far along.
Oh, awesome. So we're going to move to the next speaker, and I think Nicola Malega has joined us, and he's going to be giving us an overview of ESA's Earth Observation Upcoming Small Satellite Missions.
Yes, thank you for that. As the title of the paper says, this is a fairly generic paper that is here to present some of the work that is currently being done by ESA in the context, actually ESA Earth Observation Directorate, in the context of small satellites. And what we wanted to present was to try to give you a panorama of what ESA is trying to implement and in which ways. And from the presentation, we tried to give an idea of the 3 main project lines that we have that are involving a small satellite, ranging from, let's say, the smaller missions, like the one involved in FISATs. Those are the smallest CubeSats with the focus on onboard artificial intelligence. Then we have a second group of mission called Scout, which is actually, let's say, it started at the end of last year, and then right in between the whole COVID-19. They were set to end in June. They will actually, let's say, take one additional month to complete. And one of the 4 candidate mission will be selected and is going to be implemented in the next 3 years. So this is going to be kind of a full-fledged mission, so 3 years of operation with a very small satellite, so very challenging and very interesting kind of mission. And then the last one, it's another, let's say, container, which is called Incubed. This is a very generic container of projects, but it also involves mission, including nano and small sat. And we are presenting 2 examples of that. One is 12U CubeSat with onboard AI and the ability to do super resolution on board, which is very interesting. And let's say on the other end of the spectrum offered by Incube, we have another mission called Sat4EO, which is a 250 kilogram spacecraft that will offer a very high resolution in the order of 0.6 meter native. So once again, a very challenging and interesting implementation of say very capable optics on board of a small sat.
Question for you with respect to your category of Earth Explorer. And
yes.
I'm intrigued by how fast you guys can put a mission together and get it launched. What is the normal time for these opportunity missions from authority to proceed to launch?
Well, Scout is a new thing, and it was designed, and it is designed to be fast with respect to other very big institutional mission. So I think that the old time from, let's say, the opening of the bid, which is the typical way ESA relates with industry. So we have a call for proposal, and the set of proposals are received from industry. So starting from the issue of the proposal and to the launch, it will be 4 years, more or less.
Okay, thank you.
You're welcome.
Next up is we're going to have a presentation from Andrew Santangelo, and he's going to be talking about the CANOP CubeSat mission, which is remote imaging of the rainforest and testing AI-based identification tools.
Hello, everyone. Good afternoon. I hope everyone's doing well and staying safe. My name is Andrew Santangelo, and I'm Chief Technology Officer of SciZone, and part of this helping out Carthage College for the CANOP CubeSat mission, which is a student-based CubeSat mission. With its original purpose was to actually do remote imaging of the rainforest and to test out multispectral camera system on a 3U CubeSat. And then since then, it's involved also including not only the image capture, but also imaging of urban areas to see the change due to LED lighting, and just to image that in a more broader range of frequencies, and also start testing out some AI-based tools that is part of our the LinkStar radio system to do identification of targets, test targets on the ground. And this started as an undergraduate mission, and of course, like everyone's talking about, all the students have graduated. So, but my goal is to take the ball and get it to flight here, and because part of the role for SciZone is we're providing, turns out, the flight software, the radio system, both the beaconing and the duplex system. But we still are focusing on using the Spectral Devices imaging system to do a form of push broom Landsat remote imaging in near infrared, and do over 60 kilometer swaths from an orbit of 400 kilometers. The CANOP mission is gonna, I think we're looking at going up in December. COVID will determine all that, right? So sometime soon, I'm feeling good about that. and it'll be launched from the ISS. It's an Alana mission. And it's, again, its primary mission is to imaging of rainforests, select rainforests. And we have geofences set up because, as you can imagine, the cameras draw a lot of power, or the camera draws power, so we turn it on, turn it off, and go from there. But also, we do want to try and capture other things. And one of the other is the, again, key cities with LED lighting. And then the last piece is there's been some interest of imaging larger targets in flight, 737s and larger, and having the AI tools aboard the Link-Star radio system to recognize it instead of sending the image to the ground, which eventually will do, but to notify, hey, we detect a target and it is doing something. So where you can get that message out rapidly to the ground, and then you can bring all the larger data down later on. And so it's been an exciting project, and again, my goal is trying to help get this over and help Carthage College get this from students graduating, good thing, that's good, we like that, to flight and in orbit, but also to demonstrate a lot of these technologies, which will lead them to the next mission. And hopefully for Carthage and for other universities, a lot of these roadblocks will be more turnkey that we can provide to the community, because all the software is going to be shared, and including the tools for imaging, communications, satellite control will be open to the community.
Okay, I had one preposition question for you, but I see one from the audience that I find interesting, and it's from Deepak, and I think Deepak is still with the Aerospace Corporation, but he's asking this question. He says, I noted with interest your intention of studying urban nighttime light signatures, in particular the move to LED technology and away from high pressure sodium and other lighting types.
Yes.
Given the Landsat Experience Imaging, Las Vegas, the brightest city on earth, how does your push broom imaging system accomplish the nighttime mission versus the readily attainable daytime multispectral imaging system?
And to be honest, I'm working that problem too. I can't answer that, but my interest is in trying to focus on specific frequencies and change the focal length probably for the image at night. And I don't think we're going to be picking Las Vegas though, top of my head, though I do think we're looking at Chicago. We're looking at smaller cities too, and just to see the change from day to night. And the Spectral Devices camera is a push broom imager, but you can also do change its imaging or how it images to the system. And let me add one other thing we're doing different. I mentioned is we're also taking a lot of thumbnails, right? Or we're taking, there's a picture and then the thumbnail is sent to the ground. So if there's an image that's not satisfactory, or we have to change it, we say, oh, that thumbnail isn't good. Let's change the parameters and adjust that, and then bring, once we do get an adequate thumbnail, then we can bring the larger image down.
Okay.
That answers the question.
We're going to move to the next speaker. We're going to come back. We're going to have some more questions, but the next speaker is, I'm going to find his name again because we had a change, is Nobutaka Fukushima, who is going to be talking about the engineering model development of Hibari, a microsatellite for technology demonstration of variable shape attitude control.
Hello, good morning or good afternoon to everyone around. Sorry for the sudden name change. I'm Nobutaka Fukushima. I'll be talking on behalf of Kay. I'm one of the, I'm part of the Hibari team as well. Anyways, the Hibari is a 40 kilogram microsatellite class satellite. The main technical mission is the demonstration of a novel attitude control system called variable shape attitude control, which consists of 4 pedals around the satellite, 1 on each side. And by moving those pedals, we're hoping that we'll be able to change the attitude faster than a reaction wheel, what reaction wheel is capable of. And this variable shape attitude control, we call it VSAC to abbreviate it. This is proposed by one of our professors in Tokyo Institute of Technology. So basically this VSAC is based on our idea to utilize a reaction torque generated by changing the shape of the satellite itself, which is used used by the paddles around it. And this Hibari is planned to be launched in 2021, somewhere around July, hopefully. And this is under the Innovative Satellite Technology Demonstration Program, which is led by the Japanese Space Agency, which is called JAXA. And we are currently developing the engineering model of it. And I hope those are described in the presentation. Sorry if it's a bit brief, but.
No, that was perfect. I do have one preposition question for you, and it has to do with, I was fascinated with the talk, and I could see the shapes changing as you're managing attitude control of the spacecraft. What did you also look at anomalous conditions in which you lose one of the arms? What effect did that have on the control mechanisms for the spacecraft when you lose one arm?
Oh, okay. That's it. I'll quickly switch to because I actually got Kay in my iPad in a separate line, separate chat. So I might give him a question if that's okay. It'll be in Japanese, so sorry.
No worries. Yeah, hang on to that question because we'll come back as you're doing the transposition there.
その時はどう対処するんですかとか。Wait, so basically, if one of the paddle loses its function, so for example, it'll be, so if it's running on like 3 paddles or 2 paddles, okay.
Yes.
まあ、一つのパドルが誤作動して、一つや二つのパドルが誤作動して、その全く動かない状況になってしまったら、どう対処するんですか？
今回は、セーフモードに行って、リアクションオイルとかでとりあえず対処する。
了解です。So, for this case, for our case, we'll be shifting to what we call a safe mode. So which will pretty much lose the function of the VSAC, and we'll be just mainly using the reaction wheel for attitude control.
Okay. And Philip Rittmuller had one more question that I will provide in this case is the torque, he says, is the torque coming from aerodynamic forces, solar pressure, gravity gradient, or all three or others?
Yes, I believe so. Hang on a sec. I think those are inside the presentation. Yes, it will be from, as you said, the, sorry, I didn't.
Solar pressure, gravity gradient. And
yes.
He mentions also aerodynamic forces.
Yeah.
Yeah, 全然聞き取れないわ。
お。
ごめんね。
Yeah. Wait, so I couldn't get
his question was, is the torque coming from aerodynamic forces, solar pressure, gravity gradient, or all three?
Oh yes, it's all 3 of them. Yes, sorry.
Okay. All right, thank you. Well, hang in there. We're going to be coming back with more questions later. Thank you.
Yep. Awesome.
And
thank you.
Our last speaker in this session is going to be Walter Holmans, who's going to be talking to us about a mission revived, lessons learned from Starshine for redesign, assembly, test, and integration.
Hi, thank you, Roger. Starshine stands for Student Tracked Atmospheric Research Satellite for a Heuristic International Networking Experiment. It's essentially a disco ball where each of the mirrors is made by a student or a student team around the world. So when the disco ball is spinning, the sunlight will reflect and they can see their handiwork twinkling from the heavens. And they would record their observation, the time, and telemetry that to a central location so that the students will be part of the observation network to detect the decay of the orbit due to the upper atmospheric density. So in that sense, it's a student-built weather satellite. It's built by a volunteer group of students, research engineers, and educators, and it's led by one of the founders of this conference, Gil Moore. The project goals were to measure the upper atmospheric density by the student observation of the twinkling mirrors, to flight validate an RFID tag that was supplied to us by one of the companies. And so when the satellite passes over the radar fence, not only do they detect the satellite, but they get an indication of exactly which satellite it is. And then the last goal was to flight validate one of the products my company makes, the Advanced Lightband, and to help us validate the integration procedures. It was on the maiden launch of the Launcher 1 from Virgin. It didn't quite make it into space. But we did have a lot of fun with the project, and we learned a lot. One of the things we learned with the volunteer space project is some essential things is the mission's got to be inspiring, and it's got to be fun. It's got to be very, very simple. This satellite had no RF transmitters or receivers. It was passive, and it had very simple science methodologies. We were very well connected. Gil Moore knows a lot of people in the industry, and he could help push us forward and push us onto a rocket. And then we had a lot of companies that donated a lot of the hardware and the time and the expertise. We learned that shipping damage is a risk. The satellite dropped off the loading dock while in its shipping container en route to the launch site. So we had to fix that in the field successfully. We managed to use air bearings to verify that the satellite's rate of rotation was the 5 degrees per second to produce the most effective twinkling. And then we learned that for the future Starshine missions, we can 3D print the whole thing and make a much simpler, perhaps even lighter spacecraft. That's my summary.
Thank you. I know we were all watching online as the launch was occurring that day, as the 747 was out doing its pattern, we're getting ready, and then we were hoping for success. But I know that you had a lot of students that were involved in this mission, and I know they had to be disappointed. So did you guys talk with the students afterwards, after the failure of the launch vehicle?
Well, other than convey, we did our best, and we understood that there's risks in getting in flying on a new launch vehicle. I think they understood that. What we could offer them is that the Starshine program will continue, and there will be an opportunity to make another chance. The Starshine program itself, this is the 4th satellite. So Starshines 1, 2, and 3 worked. Some derivative programs called POPAX also worked. I think we've been rolling the dice to some extent on this program, and sooner or later things didn't quite work out for us. It goes with the territory. It's unfortunate that the students had to have that experience, but that's space exploration for you.
Yep, space is hard, that's for sure. So let's go back to Ensign Ansley Knight. And so Ensign Knight, we have a question. It says, what verification methods will be used to verify the task completed by the robotic arms?
Okay, so essentially we have 3 defined mission objectives for the REX to undergo. And so the first one is that it should be able to accurately touch a target repeatedly using the end effectors. And then the second is that the arms are supposed to be able to hand off from one arm to the next without dropping the object or letting it fly around in space. And then the third is that it should be able to inspect an object on all sides by using the body camera attached. And so to verify that, we have a series of tests that we're going to conduct while on board the space station. And so a lot of that entails using both the the cameras on the REX using the end effectors in the body camera, but also we have 2 external cameras that will allow us to view the REX in motion as we're able to verify that the arms can actually, touch the target or hand off the target and things like that.
I had one more question for you with respect to your experiment. I know you're going, at the end of it, you're going to jettison it from the International Space Station. Was there any consideration on perhaps bringing it back on one of the capsules? Because some of the capsules that do resupply the International Space Station do bring back other experiments. Was there any consideration of doing that so that perhaps follow-on classes could do more modifications to it or learn from it?
So for now, the time that we have on the space station, we haven't quite sorted out how long it'll be there. But essentially the algorithm that we have an uplink, so we're able to adjust and adapt our algorithm as needed. If we see that a test isn't working right or something's not working, we can fix that and then re-upload. But essentially, this is just like the second iteration for what we're looking for. So eventually we want to be able to have that free flyer form CubeSat in space. And so we'll try to get, essentially make a new one after this iteration is complete and we have the testing that we want or need in order to build the next iteration.
Okay, thank you. Back to Bill Denninger, can you tell us more about I think you have 41 objects that you are intending to observe in your 2-year mission. Can you tell us more about those objects? Did we lose Bill?
Hello?
Yes, Bill, go ahead.
Okay. Those 41 objects were defined by the science team. They've selected objects that are known with known locations on the sky to do the specific observations with. And what they're looking for is polarization. The only known object that has definitive polarization is the Crab Nebula, so that's clearly one of the main objects. It also is a fairly high data rate object. Those 41 objects will be examined during the first year of the mission. Obviously, that's 365 days. What that tells you is that to properly do a X-ray mission, you need to look at targets for a long time. And we have targets that we look at for up to 2 hours and several that we look at for up to 14 days continuously to collect enough data. Because what you're looking to do is get enough X-ray photons to do the statistics on them to understand what their polarization degree and angle is. So they're known targets on the sky.
Okay.
The second year of the mission will open itself up to other targets, targets of opportunity and that sort of thing.
Awesome, thank you.
Yep.
There is a question from James Torley to Walter Holman's on the Starshine mission, and he's asking, how much of an impact to ground-based astronomy is Starshine?
That's a terrific question. The surface area of a single mirror is about an inch squared. So it's with respect to, say, some of the Starlink satellites, it's got a reflecting area that's several orders of magnitude lower than the larger satellites. Naturally, we designed the mission to minimize obscuring the stars, but we did in fact use the starshine, as a means to conduct the science. So we were literally measuring the effect we were using the sunlight to measure the effect of sunlight on the upper atmospheric density. In addition to that, the mission was designed to deorbit within 3 months, so that after the experiment was done, we would no longer be a burden to the clear sky.
Okay, thank you.
Sure.
And for the Habari team, there's a question from Rigoberto Reyes, and he asked, do you think that VSAC can be used, VSAC, can be used in a small satellite such as a 3U CubeSat?
Oh, okay. So a much smaller satellite like 3U size CubeSat. I will quickly ask Kay. Kay さん、渡辺さん。
はい。
3U キューブサットとかちっちゃいやつにも VSAC が使えると思いますか？
使えるけど、
はい。
パドルはその場合2本とかになりそう。
はい、了解です。So it is possible for a 3U size CubeSat to have VSAC. However, due to its size constraint, you could probably possibly use somewhere like 2 paddles instead of 4, and still do the similar attitude control.
So for a smaller satellite, you can use fewer pedals to effect control on the attitude of the spacecraft if the spacecraft is smaller?
Yes.
Okay.
Yep.
All right, thank you.
Yep.
Let's go back to Andrew Santangelo. I noticed 3 national parks or 3 jungle areas that you picked for your experiment. Can you tell us what the rationale went into picking those 3? Were there others that were considered as you were picking?
Yeah, and unfortunately, I'm the vehicle hardware guy that was based on the student teams, and their focus was on regional climate, weather patterns, latitude, and the terrain. And they wanted to get, and of course, part of it was the orbit too, correct? Because they're combined with the orbit, same orbit as the space station going down. So it was more focused on rainforests and kind of getting a broad coverage if they could between the different continents, based on what I've seen. And of course the goal is they'd have the data to study. They've graduated, but other students and themselves can view it. It'd be open to the community. But I think that was the main target. They want to be in a rainforest and look at regional climate and weather patterns in distinct different regions of the Earth.
Interesting. I was wondering if they considered the tundra or the northern parts of Siberia as part of their target area.
Yeah, and to be honest, I asked that question too, to go, because this is a lot of potential. And when you see the parts added with the LED lighting and the targets on the ground, that was my addition after the students came on. And along with the interest, there was an interest on the tundra. And I think it's just partly the limit for the student team to capture and focus on the problem that they wanted to do for this mission. And to be very honest, for a CubeSat mission for undergraduates, especially something like this, a 3U mission doing multispectral imaging, what I explained to the students, if they get in orbit, that is a major accomplishment. If they get their satellite to say hello world, they've done a lot more than most people have done. Okay, if we get a picture of one rainforest, they've knocked it out of the park. And so I'm not trying to be cynical, but it's a major accomplishment from being 18 to 21, 22 years old to build a satellite to do multispectral imaging, and they learn all the problems that go into something like that. And it is actually a very interesting problem, because a lot of students ask, well, what can we do? Everyone's done everything now. Well, we still need to measure. We still need to learn. We need to still explore and continue. This data fits in the pool of data for all scientists out there. Even if we get 1 image or we get 100 images, there's going to be much value to this.
Yes, I found it's an amazing spacecraft that you guys put together.
Yes, thank you.
We're going back to Maddie Garcia with MIT on the Beaver Cube, and there's a question from Deepak of Aerospace again, and it's, were the Beaver Cube microbolometers subjected to any radiometric calibration procedures on the ground, and are there plans to document this?
Here we go. Yeah, actually, we're currently finishing up building our 4-bar target for MRTD testing of both of our microbolometer cameras. One will be modified. One has a filter in front of it, or filter sandwich in between the lens and the sensor, and one with the unmodified FLIR LWIR camera as well. So we're hoping to go ahead and get that rolling as soon as possible. we will be documenting. We're actually pulling all of our data into a wiki. So hopefully we can make this publicly available for other teams also interested in developing CubeSats on our order as well.
Oh, thank you. So we're going back to Nicola Malega with ESA and a question on FESAT-1. Can you give us a little more information about, you indicated in your talk that this is the first, you believe, use of artificial intelligence / machine learning in a CubeSat class mission. Can you tell us a little bit more about how it's being applied?
Well, I'm not directly involved in the mission, so if you have specific answer, please just send an email. I will redirect it to my colleagues. But as to the best of my knowledge, this is the first application of of deep learning and convolutional neural network on board using let's say, applying this algorithm on dedicated artificial intelligence hardware on board, specifically at the use of the Movidius board, which is a kind of GPU, very low power GPU, which has been applied to the multispectral, actually hyperspectral payload, which is made by Cosine in the Netherlands, which is called HyperScout. And clearly the whole idea is to perform cloud detection, and so to, let's say, have a much more efficient transmission of data to the ground.
Okay, there's, thank you. And there's a question for Maddie again from Michael Miller. And his question is there some synergy between the thruster operation and the imaging experiment, or are they independent?
Yeah, so these are actually independent. We're planning on firing the electrospray thrusters at the end of the mission in order to not interfere with the imaging portion of the mission. There is potential contamination possibility with the electrospray thrusters because they're using an ionic liquid propellant. So in the event that, for whatever reason, the propellant contaminates the lenses, we want to make sure that doesn't happen. So we're doing these experiments separate.
Okay, thank you. We brought up artificial intelligence and machine learning just a moment ago with Nikolai. We're coming back to Andrew Santangelo. Can you give us more insight into your deep learning on Canop?
Yeah, I can start getting to a little bit there, and it's a little more of a last minute thing because we've been working with our Linkstar system, adding deep learning and machine learning and artificial intelligence to our Linkstar system, with the whole idea, the concept being, you have a lot of data coming in, and how do you quickly get that down? Well, you put the learning onto the CubeSat. So we're starting to use Bayesian networks as part of our tool for part of the identification. Of course, we're trying to do this on a 3U CubeSat, right? And our first target, and this is a late entry, was we were asked to identify 737s or larger in flight, and that's of interest to various parties. So the trick is to how do you get that information to the ground rapidly, not sending gigabytes of image files and what have you. And so what's happening is we're putting in it's called a QuickSat perception tool, autonomy tool, that's going into Linkstar, and it'll look for, we teach it, look for a target. And instead it'll initially send a message then to the ground saying, hey, I found something. Maybe send in your bigger birds or aircraft or ground stations to look for that target. And that way, the goal is to provide that, so it's learning on the ground and in space, but also providing a way to rapidly get that discernible knowledge then to the ground. And of course, a variation of this that it won't be ready for this mission is to, instead of detecting faults when they happen in a satellite or on the ground or in the proximity, that your machine learning system is learning, hey, we may see a trend here, our 50% chance of failure using our Bayesian tools. or 80% chance of failure, you may want to look at your sensor. And actually, we're starting, I don't know if you can see this, starting with a little BeagleBone Black AI even playing with that. But we're also looking at larger processors. The only thing I'm seeing early on is heating. This gets really hot if you put it to especially image processing on the CubeSat. So, so it's a problem we're looking at right now. And just so happened, CanUp was on the queue, so that was added to the satellite, and it has a multispectral camera. How about that?
Thank you.
You bet.
So, and coming back to Ensign Knight, there was what comes next after this experiment is completed? Do you have some first year, second year midshipmen starting to develop some new concepts for what comes next in pursuit of a robotic spacecraft that performs either inspection on space or on-orbit assembly?
So essentially, after this iteration, our main goal is to have a sort of autonomous free flyer form CubeSat that is capable of assembling parts in space. So hopefully we'll be able to send up a type of like a bin of parts that the CubeSat will be able to assemble while in space.
Okay, thank you. And I think earlier you mentioned COVID-19 impacts for your organization. Are you guys still seeing, how are you handling the your new class that's coming in? What are the impacts for you guys assembling, or how are you conducting classes there at the U.S. Naval Academy in this environment?
Well, so that's still to be determined. I think a lot of it is going to be a online hybrid type effect. Like I said, I graduated in May, so I'm basically working at home with the team, but furthermore, they're slowly allowing the midshipmen to come back on the yard, so they'll probably have school starting in the fall, but it's definitely going to be different from normal circumstances.
Okay, thank you.
Mm-hmm.
Coming back to Maddie Garcia, is there any significant improvement in the green propellant technologies that can replace toxic hypergalls like hydrazine? Do you think the electric propulsion is a viable alternative? And that's coming from Gokul Ravi.
Yeah, that's a great question. So the difference with electrospray thrusters and something like a hydrazine, like hydrazine engine, the issue is that you have different ISPs. So with your electrospray engines, you have like really high ISPs, like in the like 1800, 1900 Newton seconds, and you have a lot lower ISPs with the hydrazine thrusters. So it's really dependent on your application, because if you need like a much faster, basically a higher amount of thrust for a shorter amount of time to get somewhere really quickly, or to get that delta V that you need to get out of orbit, you might need to use a hydrazine thruster of an electrospray. So electrosprays currently are in the market to do very slow orbital altitude changes because they have really high ISPs. So it's really, really low thrust over a really long period of time. So it's kind of dependent on your application. So really, I don't know if electrosprays will replace some of these really high-powered operations.
And there was a follow-on question for you from Andy Hoskins, and I think we may have covered one of these questions before, but I'm going to, at the risk of repeating it, here we go. One is, how long and at what thrust do they plan to operate the tile system at the end of the mission? And he also asked, how much altitude change do they hope to accomplish? And I think it's not very much from altitude changes, maybe like 280 meters or something like that, if I remember correctly. But yes. Go ahead and answer the rest of the question, please. Thank you.
Yeah, so it'll fire at 50 micronewtons. So as you can see, really, really small thrust for 3.5 hours. So like you would see in comparison for any of the like second stage engines that you see on rockets, they fire for maybe like 8 minutes as opposed to 3.5 hours to get out to the orbit that you need to get to. So we're really, really small and slow. And then altitude change, as mentioned earlier, is hopefully 280 meters if we have all the right conditions. We do have a pretty coarse attitude control system for using magnet torquers. So we don't have the fine control as a reaction wheel. So hopefully we're pointing in the exact, opposite direction of our orbital velocity. If not, it'll probably be a little bit less than 280 meters.
Okay, thank you. And this next question is probably going to go to several of you on this panel, and we'll let you decide who wants to go first, but I'm going to probably pick on Bill Denninger. Are there any government regulations or processes that you would have liked to see streamlined that you found a little burdensome as you're getting ready to launch your mission? I think we may have lost Bill. Bill, are you still there with us? Let's try Andrew Santangelo, same question. Andrew,
Yeah.
Are there any government regulations or
ready.
processes that you'd like to have seen streamlined or improved to help you get up in space?
Yeah, and part of it is, with our radio system, we work with the FCC and NOAA, putting the radios and the flight systems up. And of course, we're doing imaging, so it involves NOAA. And one of the things that needs to be streamlined between NOAA and the FCC, because a simple example, NOAA asked about how all the security with the images we're transmitting from the satellite to the ground. And of course, it's like we're using basically an internet connection through the satellite network, Globalstar network. The satellite's tree is a node on internet. And they asked me, well, we need to know what your security plans at all the ground stations, your card readers, do you have a fence? And I'm like that's like asking the security of AT&T and all their ground stations. You're asking the impossible. And after a little back and forth, they thought that maybe that was a bit unreasonable to ask that. But there was just more time to go over, do you really want the security of every ground station of Globalstar? Do you really want the things like that? So, and of course with the FCC, and I understand they're getting overwhelmed on that side, but I wish there was just better tools and more streamlining and something that didn't look like circa 1990 that we're working through.
Okay, thank you. And let's see, I think Bill is still there. Bill, do you have a quick minute to respond?
Can you hear me?
Yes, go ahead.
Oh, now you can hear me all of a sudden. How weird. We're in the process of going through all the builds at this point, so we haven't seen any big regulations come up that I think we'd like to see streamlined here in the near term.
Okay, thank you so much. And we're getting close to the end of our time, and I'm going to thank all of the speakers, but I'm going to turn it back over to Charles Swenson so that he can wrap up for us today.
Thank you, Roger, for running our panel. And I'd like to thank all of our panelists and encourage you that to go out and take a look at the papers themselves that are on the Small Satellite website. And this concludes our panel, session 5, Next on the Pad. Thank you all.